Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, you can find a way to do this at smarturl.it/help-ISU-actuary. Here's the problem for today. It's a written answer problem from the last exam MLC, problem number 2 in the written answer part. Consider a special 10-year deferred, 25-year endowment insurance policy sold to Zach, who is 40 years old. The policy pays no benefit in case of death before age 50. A death benefit of $100,000 is payable at the time of death in case of death between ages 50 and 75. In case of survival to age 75, Zach will receive a benefit of $50,000. You are given that mortality follows the illustrative life table. Interest rate is 6%. Note that that's the interest rate that is used for calculation of actuarial present values in the illustrative life table. That's an important thing always to note. Deaths are uniformly distributed over each year of age. Part A asks you to write down an expression for the present value random variable Z for this insurance in terms of T40, the future lifetime of a 40-year-old. And it's the random present value of the benefits Z, of the benefit paid in this policy that you need to express in terms of the future lifetime of a 40-year-old. Part B is asking you to sketch a graph of the present value of the benefit as a function of the time of death, and clearly label the axis and show all the key values. Part C asks to calculate the probability that a single premium of $15,000 will be sufficient to cover the benefit payable under this policy. Part D asks to calculate the smallest single premium that will be sufficient to cover the benefit payable under this policy with a probability of at least 60%. And finally, Part E asks you to calculate the expected present value of the benefit for this policy. So for Part A, we have the benefit is 0 if death occurs during the first 10 years, because there is no death benefit then and there is no survivor benefit. So there's 0 for T40 less than or equal to 10. Then it's 100,000 death benefit, so its present value is 100,000 times 1.06 to the minus T40. And that's for T40 between 10 and 35. And then once this person survives to age 75, there is a one-time survivor benefit payable at age 75, also 35 years into the future, and its present value is 50,000 times 1.06 to the negative 5, or approximately 6,505.26. And this is paid anytime the future life expectancy of this person exceeds 35 years. That's why the formula looks like this. And here's Part B, the graph of this present value of benefit, and it's 0 for future lifespan being between 0 and 10. So you see that part where Z is equal to 0. Then Z is equal to 100,000 times 1.06 to the minus T40. That's the downward sloping curve in the middle part between 10 and 35. And I note the points that are at the two end points of that curve because they may be useful. So if for future lifespan of 10 exactly, the point on the graph is 10 and 55,839.48, which is the present value of death benefit of 100,000 calculated at 6%, discounted at 6%, 10 years from age 50 to age 40, which is the age at which the policy is issued. Then the other end of this downward sloping curve corresponds to the death occurring just a nanosecond before reaching age 75, 35 years into the future. And if there's a death payment, then its present value is 13,010.52. But if the person survives, then the present value drops to 6,505.26, because instead of $100,000 benefits, 50,000 endowment benefit is paid. And then, of course, beyond 35 into the future, so age 75, the present value is always the same, because the payment is actually made upon survival to age 75. Now, in part C, we ask about 15,000 being sufficient to pay the benefit for this policy. And the present value of death benefit can be more than 15,000, only within some range of values between of T40, between 10 and 35. But to find that specific range, we need to first find where Z is equal exactly 15,000. And this happens when 100,000, present value of 100,000 payment is exactly 15,000. And that happens at age 32.558015. So we note that because Z is decreasing between 10 and 35, Z will be greater than 15,000 if and only if T40 is between 10 and that age we just calculated, 32.558015. So that the probability that Z is less than or equal to 15,000, which is the probability that a single premium of 15,000 is sufficient to cover the benefits, is 1 minus the probability that Z is more than 15,000, which is 1 minus the probability that T40 is between 10 and 32.558015. And in terms of values of the population size, based on mortality table, that's 1 minus L50 minus L72.5588015 divided by L40. Now, L50 and L40 are given in the table, and we can use linear interpolation between L72 and 73, and it will be precise because we are told that uniform distribution of deaths between the year of death, in the year of death rules. So at age 72.558015, we are approximately 0.558015 of the way into age 73, but 1 minus that still in age 72, roughly. That's what this linear interpolation that you see here says. And then we just plug in the numbers from the illustrative life table and do the calculation, and we get approximately 0.6861922. So for part B, we note that there is a range of ages when the present value of policy benefit is 0, the smallest possible. And that happens if the person dies within 10 years from age 40 when the policy was issued. And 10Q40, the probability of that is 1 minus 10P40, or 1 minus L50 over L40. Based on illustrative life table, we can plug in the values of L50 and L40, and we get that this is 0.0388982. The next smallest value of the policy benefit is the present value of the endowment benefit, which we know to be 6505.26. Now, what is the probability of paying that much? Well, it's the probability of surviving 35 years from age 40, which is L75 over L40. And that's based on the illustrative light table, we plug in the numbers, and that's 0.5794035. Now we see that the sum of the two probabilities is more than 0.60 already. So the smallest single premium that will be sufficient to cover the benefit payable under this policy with a probability of at least 0.60 or 60% is the single premium equal to the present value of the endowment benefit. Now the zero death benefit doesn't need any premium, that's true, but a zero premium for that, plus the endowment benefit, so 6505.26. Now, the expected present value of the benefit under this policy is basically 100,000 for a deferred term life insurance, fully continuous, issued at age 40, deferred by 10 years, and then good for 25 years after that, plus 50,000 one-time endowment benefit for survival to age 75. The endowment benefit, we can just calculate this 50,000 times L75 or L40 times 1.06 to a negative 35, plug in those numbers and get that value. The 10E40 is actually in the table. It's 0.53667. So we plug that in, multiply by 100,000, we get 53,667 times that term insurance single benefit premium that we need to figure out, plus the premium for the endowment benefit based on the 50,000 times 35E40. Now, how do we calculate A bar 50 colon 25 per 1 over 50? Well, we note that we are told that uniform distribution of deaths rules. So A bar is equal to I over delta times A. And then we write this term insurance as A50 minus 25E30 times A75. And we actually can again calculate it 25E50 as L75 or L50 times 1.06 to negative 25. And A50 and A75 are given in the illustrative life table, while I over delta is 0.06 over natural logarithm of 1.06, so all the numbers can be plugged in, and we get 0.1709835, multiplying it by 53,667 and adding the 3769.17 roughly, we get 12,945.34. Please remember this is copyrighted material. Past problems from Society of Actuaries examinations belong to the Society of Actuaries and are reproduced with permission, but the solutions are mine. Good luck in your studies and good luck on the test.